Hey there, science fans! Welcome to our crash course on the periodic table, designed to help you ace your 10th board exam. Today, we'll break down the essential concepts you need to know, from its ingenious organization to the fascinating trends it reveals. So buckle up, get your safety goggles on, because we're about to embark on an adventure in the world of atoms and elements. Alright, science explorers, let's start our journey with the basics. Imagine a giant jigsaw puzzle where each piece represents a different element. Back in the 1860s, a brilliant Russian chemist named Dmitry Mendeleev noticed some intriguing patterns in the properties of elements. He realized that if he arranged the elements by their atomic mass, similar chemical behaviors would repeat periodically. Mendeleev's table was so well designed that he even left gaps for elements that hadn't been discovered yet. Over time, scientists refined Mendeleev's table, incorporating new discoveries and a deeper understanding of the atom. Today we arrange the elements by their atomic number, which is the number of protons in an atom's nucleus. Okay, science sleuths, remember how Mendeleev noticed those repeating patterns in the elements? That, my friends, is the essence of the periodic law. It states that the properties of elements are a periodic function of their atomic number. Elements in the same vertical column, called a group, share similar characteristics like being super-reactive or preferring to keep to themselves. On the other hand, elements in the same horizontal row, called a period, share the same number of electron shells, which are like energy levels for electrons whizzing around the atom's nucleus. Each group and period tells us something unique about the elements within it, making the periodic table an incredibly powerful tool for understanding the building blocks of matter. Let's dive a little deeper into the layout of our periodic table neighborhood, shall we? Remember those vertical columns we call groups? Well, each group represents a family of elements with similar chemical properties. Take group 1, for example. These are the alkali metals like sodium and potassium, and they are notoriously reactive. Drop a chunk of sodium in water and watch out. It'll fizz and react violently, wanting to give up its single valence electron. Now scoot over to group 17 and you'll meet the halogens, like chlorine and fluorine. They're one electron shy of a full outer shell, so they're always looking to steal an electron from someone else. And finally, we reach group 18, the noble gases like helium and neon. These elements are the cool kids on the block. They have a full outer shell of electrons, making them super stable and unreactive. Now let's talk about the horizontal rows or periods. Each period represents a different energy level for electrons. As you move across a period from left to right, you add one more proton and one more electron to the atom. This increase in positive charge in the nucleus pulls the electrons in tighter, affecting the atom's size and how easily it loses or gains electrons. Now that we've explored the neighborhoods of the periodic table, let's talk about the trends we see as we travel across and down this amazing chart. First up, atomic size or atomic radius. As you move across a period from left to right, the atoms actually get smaller. That's because you're adding more protons to the nucleus, increasing the positive charge. This stronger pull reels in those electrons, making the atom more compact. But when you move down a group, it's a different story. Atoms get bigger as you go down because you're adding more electron shells. Next, we have metallic character, which describes how easily an element loses electrons to form positive ions or cations. Metals, located on the left side of the periodic table, are like the generous folks in the neighborhood. They're always willing to share their electrons. Nonmetals, on the right side, are more electronegative, meaning they'd rather gain electrons to form negative ions or anions. Electronegativity follows a similar trend to metallic character. It increases as you move across a period and decreases as you move down a group. Fluorine, that highly reactive halogen we met earlier, is the most electronegative element, while the poor alkali metals down in the bottom left corner have the lowest electronegativity. Finally, we have ionization energy, which is the energy required to remove an electron from an atom. The higher the ionization energy, the harder it is to pry that electron away. As you might expect, ionization energy increases across a period and decreases down a group. The periodic table isn't just about neat rows and columns, it's also about the amazing diversity of elements. We can broadly classify elements into three main categories: metals, nonmetals, and metalloids. Metals, those generous electron donors, are the life of the periodic party. They make up the majority of the elements and are found on the left side of the table. Think of shiny silvery metals like copper, gold, and iron. Metals are excellent conductors of heat and electricity, which is why we use copper in electrical wiring and iron in cookware. They're also malleable, meaning we can hammer them into different shapes, and ductile, meaning we can draw them into wires. On the other side of the table we have the nonmetals, the electron-hoarding introverts of the periodic world. Nonmetals are generally poor conductors of heat and electricity, and they can be gases, liquids, or brittle solids at room temperature. Think of oxygen, the gas we breathe, or sulfur, a yellow solid. And then we have the metalloids, the fence-sitters of the periodic table. These elements have properties that fall somewhere between metals and nonmetals. Silicon and germanium, for example, are metalloids that are essential components of computers and other electronic devices. We've already met a few of the special families in our periodic table neighborhood, but let's take a closer look at some of these unique groups. First up, the alkali metals, group 1, are the most reactive metals on the periodic table. They're so eager to lose their single valence electron that they're never found in their pure form in nature. Sodium, for example, reacts explosively with water, which is why we store it in oil. Potassium is another alkali metal that's essential for plant growth. Next door in group 2, we have the alkaline earth metals. These metals are also reactive, but not quite as much as their alkali metal neighbors. Magnesium is a lightweight metal used in airplanes and fireworks, while calcium is crucial for strong bones and teeth. Over in group 17, we have the halogens, those highly reactive nonmetals we met earlier. Chlorine is used to disinfect water, while fluorine is added to toothpaste to prevent cavities. These elements are so reactive that they're always found combined with other elements in nature. And finally, we have the noble gases, group 18, the most stable and unreactive elements on the periodic table. Helium, the lightest noble gas, is used in balloons and blimps because it's less dense than air. Neon, another noble gas, is used in advertising signs because it glows bright red when electricity is passed through it. So, we've explored the neighborhoods, met the families, and uncovered the trends of the periodic table. But why is this chart so important, you ask? Well, the periodic table is more than just a list of elements. It's a powerful tool that unlocks the secrets of chemistry. Think of it like a chemist's cheat sheet. By understanding the organization of the periodic table and the trends it reveals, chemists can predict the properties of elements and how they'll react with each other. This predictive power is essential for developing new materials, designing medicines, and understanding the world around us. For example, knowing that elements in the same group have similar chemical properties allows us to make predictions about their behavior. The periodic table also helps us understand chemical bonding. Elements strive to achieve a stable electron configuration, like their noble gas neighbors. They can do this by gaining, losing, or sharing electrons with other elements. Alright, science superstars, we've covered a lot of ground in our crash course on the periodic table. Now let's review some key points to help you ace that 10th board exam. First, remember that the atomic number is like an element's fingerprint. It tells you the number of protons in an atom's nucleus, which defines that element. No two elements have the same atomic number. Second, those valence electrons are the key to chemical bonding. They determine how an element will interact with other elements and what kind of compounds it will form. Periods tell you how many electron shells an element has, while groups indicate the number of valence electrons. Elements in the same group share similar chemical properties. Finally, remember the special groups alkali metals, alkaline earth metals, halogens, and noble gases. Each group has unique properties that are important to know. Congratulations, science whizzes! You've mastered the periodic table. Remember these key points and you'll be well on your way to acing your exam. Good luck! Keep those brains buzzing and never stop exploring the wonders of science.